Hey everybody. So in this webcast I'll be talking about the derivation of this equation, which is known as the heat equation. And my goal is to make it maybe a little bit more approachable and less intimidating to some of you. And that's because this equation is simply based on an energy balance. What we see is that the rate of accumulation is equal to the flow of energy entering the system minus the flow of energy leaving the system plus the net rate of energy generation. So the box to the left is our energy box, and at any moment in time it contains some amount of energy. And the analogy that I'm making is compared to conservation of mass, for example. You have water flowing into the system and water leaving the system. And if the water is flowing into the system more quickly than the water leaving it, what we'd observe is, of course, is that the box would fill up with mass over time. It's just conservation of mass. Now, conservation of energy is a little bit more nebulous, but the fact is that it's just the same. We've got energy entering the system and energy leaving it. So energy can get into and out of the system by the flow of heat. So if we look at this box and think about all the ways that energy could flow into and out of the system, it helps to define a coordinate axis, where we've got the x direction in the horizontal direction, the y in the vertical direction, and the z direction into and out of the screen. So if we look at our control volume, we can define a few points. So for example, we've got position x right here, and a position x plus a really small amount, x plus dx, on the right-hand side of the cube. And we can look at heat flowing into the system from left to right, and the heat flowing out of the system on the right-hand side of the cube. And we can give these variable names. They're both qx, so the flow of heat in the x direction, and this one on the left will evaluate it at position x. And on the right, this is also qx, and in this case, it's evaluated at x plus dx. And of course we can have energy entering and leaving the system, not only from left to right, but from top to bottom and into and out of the screen, so both in the y and in the z direction. So if we look at energy leaving or entering the bottom of it and energy leaving the top of it, so we can find similar names for the flow of energy in from the bottom of the cube and the flow of energy leaving it. So in this case, we've got a location y and a location a little bit above y, which is y plus dy. So we can evaluate the flow of heat into the system at position y and the flow of heat leaving the system at position y plus dy. And of course we can do the exact same thing for the flow of energy into the screen and out of the screen by defining a position z and a position a little bit further into the screen at z plus dz. So of course I've got the flow of heat. The flow of heat coming in is qz evaluated at position z, and qz evaluated at position z plus dz. So I've got green arrows pointing into the cube and a green arrow leaving the cube into the screen. So of course all that makes it pretty cluttered. So I've gotten rid of energy entering and leaving in the z and the y directions. We can really just look at the flow of energy entering and leaving in the x direction. So what we've got is a flow of energy entering the cube in the x direction is simply q of x evaluated at x. And the flow of energy leaving the x direction is qx evaluated at x plus dx. So the question that remains now is, how do we relate q of x evaluated at position x to that evaluated at position x plus dx? So in other words, how do we make the relationship between these two? And we can do that by using a Taylor series expansion. And all we're really doing is just looking at the first order term. So what we'll get is the heat flux in the x direction evaluated at x plus dx, so you evaluate it out here, is simply the flow of heat into the left-hand side, so q of x, qx, evaluated at x, plus this rate at which the heat changes as a function of x multiplied by dx. And really all that's saying is if we know qx evaluated at position x, and we know the slope of a line, dqx dx, and we know this distance, which is dx, we can now figure out the heat flux at x plus dx. So it's simply, we're just looking at the first term in a Taylor series expansion, which just suggests a linear relationship between these two. So at this point, we're able to start thinking about the net flow of energy into the system, which is the flow of energy entering the system minus the flow of energy leaving the system. And that net flow of energy is simply Qx evaluated at x minus Qx evaluated at x plus dx. So we take this variable and plug it into here. What we're left with is this expression minus the expression in parentheses. And at this point, it's not hard to see that the differences here at Qx will cancel out, and the negative sign will just be propagated into here. So we're left with a relatively simple expression that describes the net flow of energy entering the system in the x direction. So now that we've got a handle on the net flow of energy in and out in the x direction, we can begin to look at the rate of energy generation and how we might describe that mathematically. And it turns out this is relatively straightforward. So what we've got is the rate at which energy is being generated is equal to a variable, we'll call it Q dot, and this Q dot is the amount of energy per unit volume. So we need to actually multiply by the volume of our box. And the volume of our box, of course, is simply, it's a cube, so we've got dx multiplied by dy multiplied by dz. So we've got the rate of energy generation is equal to Q dot times dx dy dz. And again, I should emphasize we're not really generating energy. We're just looking at the creation of thermal energy from some different source. And some examples of this include chemical, electrical, and nuclear sources. A chemical, you can imagine the reaction either being endothermic or exothermic, either cooling off or heating up the local region in which it's occurring. So all we're left with now, we know that the net flow of energy in and the rate of energy generation. All we're left with now is to figure out the rate of the accumulation of energy. And the rate of energy accumulation is simply the rate at which internal energy increases or decreases with time. So the rate at which internal energy changes over time. And I use a symbol U here for the internal energy. And U is the internal energy per unit mass. So you have to multiply by the mass in the cube. So if you remember from your course in thermo, the internal energy per unit mass is equal to the heat capacity multiplied by the temperature difference from some reference state. So we've got this reference state is completely arbitrary. I mean, it just depends on how you're evaluating U or how you're defining it. So the derivative du dt is simply the heat capacity times the rate at which temperature changes. And we've also got the mass of material is equal to the material density multiplied by the volume of that cube. So the mass is equal to the density times dx, dy, dz. So if we multiply the two together, we take du dt multiplied by its mass, we take this with the product of that, and we're left with this expression on the right-hand side. So before we can put it all together, we need to think about a relationship for the thermal conductivity. So the next thing we need to figure out is some way to relate the heat flux to the temperature. And this flow of energy, I may have called it a heat flux, but it's actually the flow of energy and might have units of joules per second or watts or horsepower if you're so inclined. But this is a total flow of energy entering the left and leaving the right side of the cube. So if you remember this expression, we've got the flow of energy into the left side of the cube is equal to negative K, the thermal conductivity, multiplied by the area through which it's traveling. So you've got, in this case, we've got dy, the vertical axis, and dz is the axis going into the screen. So we've got K times dy times dz. And it's also multiplied by the local temperature gradient in the x direction. And this negative sign, of course, says that heat will flow downhill. It'll flow towards a region of reduced temperature. So if the temperature is getting smaller as you move from left to right, that means dt dx is negative, and your q of x would then be a positive value, indicating that heat is flowing from left to right, or flowing in the positive x direction. So now what we've got is a nice way to relate the flow of thermal energy to the thermal conductivity, the area through which it's traveling, and the temperature gradient. So now we want to be able to evaluate this expression by plugging a q of x into this differential. So if we plug our expression for q into this differential, we've come up with this expression, and this expression can be simplified. So at this point, you might be able to see where I'm heading with this, is we've now got a nice definition for this first term, and we'll find along the way that all these differentials, dx, dy, and dz, are going to cancel out. And of course, we can develop this expression not only in the x direction, but of course also in the y and the z direction. So we've got the net flow of energy into the system in all three directions. And I think I wrote down the wrong thing up here. I did it correctly earlier. But the rate of energy accumulation is simply rho times the heat capacity, the rate at which temperature is changing, multiplied by the volume of our differential element. So now what we're left with is that the rate of energy accumulation, this term on the right-hand side, is equal to the net rate of energy entering and leaving in the x, y, and z directions, plus the rate of energy generation. And it's pretty obvious now the relationship between these expressions and the original equations. So what we'll see when you sum it all up, the differential dx, dy, and dz's all cancel out. And we're left with the final expression, the final heat equation.